All right, we've already talked about stability and condition sum, so this will be like revisited. And in particular, we want to talk about stability and condition as it applies to matrices. The one thing I wanted to point out and remind you of is that stability, let's switch here, stability is a property of an algorithm or method, and condition, on the other hand, condition is a property of a problem. So this is really, 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 really important to know the difference between stability and condition. So we've already looked at the condition of a problem when we approximated it in the first unit using a Taylor series. But now we're going to look at the condition of a linear system. So as it applies to linear systems of equations. So in doing that, I've prepared these graphics, and actually there's a few things we can know here. First, the condition of this system, you would call that well conditioned, and the sense in conditioning is how close is the system to being deficient. In other words, well, maybe first we should look over here. So if we have a linear system like this, these linear equations would be dependent. And so what we would say about this is this is rank deficient. Okay, rank deficient. This is parallel lines. This is rank deficient. If you were to reduce the system that's given by that, A would not be invertible. The matrix would not be invertible. It would be rank deficient, singular, a ton of other names. This is also rank deficient, so in this one we have one line parallel to the other line. In this line we have one line right on top of the other, so close that you can't even see the difference. Okay. On the other hand, this one is well conditioned. Well conditioned. And this problem is ill conditioned. And the notion of condition applies just as before. Okay, so if we have a small change in x1, how much change, for example, how much change do we get in the output? How sensitive is it to change in the output? And because these lines are very close to parallel, this is an ill-conditioned system. And we actually have good tools for quantifying the condition of a system. And so the worst condition you could possibly have would be a system that is rank deficient. So this system would be the worst possible condition you could have, and if you computed the condition number of a matrix like this, it would say it would be infinity, and this condition number of a system like this would be very high, and a system like this would have a relatively low condition number.